Hi, I'm Carrie Morton, and welcome back to this section of our Teach Out on Concussions. I'm joined by Professor Ellen Arruda, the Tim Manganello and BorgWarner Department Chair of Mechanical Engineering here at the University of Michigan. Ellen, welcome. Can you please introduce yourself and tell us a little bit about your work?
Sure. I've been working in the area of preventing concussions for about 5 years now. My work is in solid mechanics, the mechanics of materials, and how to design better with materials and structures to better protect against concussion.
So it's been reported that athletes can experience during a concussion up to 95 Gs, and that's 10 times what a fighter pilot would experience. So is there an opportunity for helmets to completely mitigate concussion?
I think it depends on the application. When you talk about Gs, you're talking about the acceleration, and one of the things a helmet's designed to do and does fairly well is to limit the force that gets transmitted to the brain from that acceleration. But there's always going to be a limit, right?
Right.
And but helmets, there's another way a helmet can, or an impact event can result in injury, and that is if the maximum change in velocity of the entire impact event exceeds a certain threshold.
Right.
So there are sort of two criterion. One is an acceleration criterion and one is a velocity criterion. Okay. And for very fast events, the velocity criterion is the important one. Slightly slower events, it's acceleration. So even if those accelerations are high, the modern helmet's been pretty good at least in the linear accelerations, at limiting what gets transmitted through the skull to the brain. I think it's in the area of the velocity change where there's a lot of room for improvement.
So Ellen, it sounds like we can't completely avoid concussion, but if in the high velocity change instance, there's a room for improvement in helmet technology. Can you tell us a little bit about how the materials can actually improve outcomes?
Sure. So what our research has demonstrated to us is that the modern helmet, which was designed to prevent the skull from fracturing, does that really well. And it does that by essentially limiting the force that gets transmitted. That's the acceleration component.
Okay.
And it hasn't really been optimally designed to also limit what's essentially the impulse that gets transmitted to the brain. So you can think of the force or peak acceleration as the magnitude of the impact event, whereas the impulse is sort of the whole duration of the event, what's happening. Where materials can play a role in helmets is to dissipate energy, and that they do that through damping vibration. And so whilst the modern football helmets, and let me just say, I think football helmets are better at this than, say, lacrosse helmets and hockey helmets. So I've looked at the materials inside those, and in an impact event, a hockey helmet is essentially an elastic structure, and it doesn't do any damping. Okay, the football helmet at least has a little bit of a hope of some viscoelastic damping. And so where we can make improvements is to understand the mechanics of that impact event, the frequency content that gets transmitted through the helmet, and design materials and structures to optimally damp those frequencies. Therefore, dissipate energy before it gets transmitted to the skull through the brain. So those are the two sort of tasks a helmet needs to perform.
So it sounds like we have a good roadmap, and that involves structures design with innovative materials. Mm-hmm. What are some of the roadblocks to actually realizing a helmet that can fight both modes for concussion?
Right. So we're dealing with polymers when we talk about viscoelastic materials, and many polymers, especially those being used in an application where their viscoelastic properties are important, actually change their mechanical properties over time to a certain extent. So one challenge is finding those materials that are optimal for the application and making sure that you don't alter that by improving the longevity of the material. Okay, so even over 2 years, helmets could start to change their mechanical properties.
And so the ideal material could actually be only effective for a year and start to degrade.
But if we're talking about the interior layer of a helmet, the padding, we could easily swap that out after a couple of years. And I think currently the University of Michigan standard is 2 years with the helmet, and then the player has to get a new one.
So we're not allowed to keep our favorite auspicious helmet
for
from
10 years?
high school?
No.
Okay, that's good.
No.
That's good news. Okay.
Whether or not it's actually being used in a game, it could be sitting on a shelf, and some aspects of the mechanical properties could be changing.
Oh, that's interesting.
Yeah.
So it's not even related to the sort of action that the helmet's seeing. It's just a true, it's over time.
Right, but if the helmet's being used over and over again, it may be suffering, microfractures and damage that render it less effective.
So even accelerating the aging even further.
Well, this is more damage, right? A damage event. And so another issue is you want to keep the helmet essentially the same size and basically the same weight, whereas adding mass would be more helpful. But, the football helmet, is pretty heavy as it is. Yeah. And by contrast, a hockey helmet's considerably lighter, right?
Right.
Much of that mass is the face mask, of course, but a lot of it is the overall size of that helmet. And the reason you don't want to go any higher in weight is because then you start moving the injury point to the neck.
And we don't want to injure we don't want to sacrifice.
You don't want spinal injuries too.
Of course.
Right.
So speaking of spinal injuries and just in general protecting the head and spine, are there other devices that that you see on the horizon that can help mitigate concussion risk?
There are. One idea that I know some folks in the DoD are working on at the Army Research Lab is to essentially more stiffly couple the head to the body. So stiffen the neck with a material that, it's called thixotropic, a material that would stiffen when a high rate event is detected. And then what that does is change the impact event from one being the head moving relative to the body to a larger mass being moved. Okay, so that changes the mechanics completely, changes accelerations and velocities, and can help mitigate concussion risk.
Do you think that's something that could translate to an athletic field?
Well, to a certain extent, I think it has, because when you look at football players in particular, they have very strong necks. They go through, part of their training is to strengthen that neck.
So that's actually not a device, but they're actually creating their own
actually creating that,
mitigation through.
Yes.
Okay.
And
that's interesting.
I remember the time when linebackers wore that huge neck brace there. I mean, that was essentially helping to stiffen the whole system as well. And yes, in general, a lot of the research that goes on at the DoD labs eventually gets translated into civilian applications.
That's quite
for sure. But they can deploy them in military applications a lot quicker, right?
Right. So for you, as we've talked a lot about the work that you're doing and the opportunities you see. What do you see in the future as sort of the holy grail for concussion mitigation in sport in terms of helmet technology?
So I do believe we can do better than we're doing right now. And it is a materials challenge. It's a mechanics challenge to keep the packaging the same size and mass, but improve the materials inside there that would make it a better helmet. It's more of a challenge for the more lightweight, hockey and soccer and lacrosse helmets that I've looked at. But it's a challenge overall. I think we can do better there, and that's what we're working on. And then the question is how much better, right? That's always difficult to know because we still don't fully understand what the cause of concussion is. We know it has something to do with axon stretching, but I'm not a neurologist, so my approach to it is to take a mechanics view and say, well, if axons are stretching, that means they're being deformed. So how do I limit the deformation? Well, I limit the things that come in that cause deformation, and that is the force and the impulse.
Okay. Well, as a parent of a young football player, Professor Arruda, I'm thrilled that you're continuing to do research in this field, and hopefully in the years to come, we'll see improved helmets that'll help to reduce the incidence of sport-related concussion.
Well, great. Thanks, Carrie.
Thank you so
Nice
much.
talking to you.
You too.